All right, here we go with more CLEP calculus practice exam questions that I found online. We're doing the second one now. Link also in the description. May or may not still be there. Who knows? It's the internet. Okay, getting right back into it. Again, some of these match exactly ones on the first test that we did, so we're just skipping over the ones that are duplicates. And we're going to go to number 26. The vertical height in feet of a ball thrown upwards from a cliff. It's not relevant. Ball thrown upwards is given by the equation minus 16t squared plus 64t plus 200, where t is the time in seconds. What is the height of the ball when the velocity is 0? Okay. So, again, our position equation is negative 16t squared plus 64t plus 200. And if you have a position equation, then the velocity is just the first derivative. So, how fast it's going, how fast it's moving from one place to the next over time. So we need to find the derivative. And this is going to be all pretty simple power rule stuff. We're going to bring the 2 down, multiply it by the 16. That gives us negative 32, subtract 1, just t. That's t to the first power. Bring the 1 down. Still have 64. Subtract 1, we get 0. T to the 0 power is 1. It goes away. And then the 200 doesn't even have a t, or you might call it t to the 0 power. 200 times 0 goes away. So that is our first derivative. That is our velocity equation. So we are asking when the velocity is 0. And, incidentally, we can kind of expect that's going to be at the peak. That's going to be at the maxima of the position equation. But we can just find it algebraically really quick. We want to know when it's 0. So we will add 32t to both sides equals 64, and then pretty easy, divide both sides by 32. T equals 2. So it happens at 2 seconds. So now that we know that time, what is the height of the ball in feet? The equation was given in feet, so we kind of ignore that part. What is the height at that time? So we go feed that time back into our original equation. S of 2 equals negative 16, 2 squared, plus 64 times 2 plus 200. So 2 squared is 4. 16 times 4 is 64. 64 times 2 is 128. And then still plus 200. And if we add that together, well, of course, 128 minus 64 is just 64. 64 and 200 is 264. So that is our answer. We look at our options. 264 is indeed one of them. So we are going to say selection E for that. All right, number 27. If the function f is continuous for all real numbers, which, again, that's just a fancy way of saying nothing crazy is happening. There's no crazy gaps. There's no crazy jumps. And the limit of, as h approaches 0, for the equation. Okay, so the function of a plus h minus the function f of just a, so all over h. So what we're doing here, this is kind of if it kind of reminds you of finding a slope or something like that. This is basically saying you're taking the function at some x value, or x is a, and then we're subtracting that from the same thing with just a little bit different x. So if h was, if we're talking, if the x value was 5, if a was 5 and h was 0.1, then the function at 5.1 minus the function at 5. So it's just a little bit of difference, and then divided by that actual difference. So it's kind of like finding the slope. It's kind of a fancy notation of finding the slope, because the difference between the x value here is the h, and then you're dividing by h. But it's tricky because we want the limit as h approaches 0, and we're really kind of saying is that's the slope. If you recognize this as being the slope, if you're finding the slope at 2 points, one point being a, where x equals a, and the other point being that a plus a little bit plus h, and then you make that h smaller and smaller and smaller until you just have the slope at a point, which is what we normally consider the slope. And that would be this would be kind of how you would do it if you didn't know how to take the derivative and you wanted to try to figure out, if you wanted to try to estimate the slope at a point, you would do something like this and maybe take a smaller and smaller. This is the kind of thing that, this is like a Riemann sum, where they teach you the Riemann sum and then say, well, we take that concept and then we turn it into the definite integral. So this is the kind of thing that they would do in the lead up to finding the slope by way of the first derivative. So let's see what it's asking us. Which of the following statements must be true? Okay, so is the function at the x value of a, is that equal to 7? We don't know that for sure. We know the slope there is 7, but that doesn't tell us that it's at y equals 7. So I don't think it's going to be that. F is the function is differentiable at that value x equals a, and that sounds like it's true, because we just said that's the slope. If we can take the derivative at that value and find that it's 7, then that certainly sounds like it's differentiable there. Let's see what else we can say. The function is differentiable for all real numbers. Well, now recall up here it told us it's continuous for all real numbers, and I said, oh, that means it doesn't do anything funny. Well, when we say continuous, they're saying that, yeah, it doesn't have any gaps, it doesn't have any jumps, but it doesn't necessarily mean, if a graph were to be something like this, and then all of a sudden it takes off like that, as it changes here from one equation to a completely different equation, unrelated, it's still continuous here. That value still exists, but you can't take the derivative there because it changes from one to another, and you have the sharp corner, and what is the slope at that sharp corner? You can't say what the slope, it doesn't have a slope because it's not smooth there. So because it only says continuous and does not say continuous and differentiable, we can't say for sure. They might be pulling something crazy. If they don't tell us, then we don't know for sure. Okay, is the function increasing for x greater than 0? So anywhere that x is greater than 0, anywhere to the right-hand side of the y-axis, is the function increasing? Well, we know it's increasing where x equals a. It has a slope of 7 there, but that doesn't tell us anything about the slope anywhere else. So we can't say that for sure. We don't know if that's it. And then the function is increasing for all real numbers. Well, that's virtually the same statement. Just all real numbers, x greater than 0. We can't say anything about where it's increasing other than at f equals a. So we don't know that for sure. So that kind of leaves us with the one we suspected before, that f is differentiable because they told us what it is. And this kind of weird one. There's no real math there. It's more of a concepts review, that kind of question. But okay, we'll take it. Number 28. Okay, here's a derivative thing. Looks like a chain rule probably. The derivative of the sine of the cosine of x is what? Okay, so the sine of the cosine of x, and we're talking chain rule stuff. So the outside equation is f, that's the sine. The inside equation we'll call g, that's the cosine. And so the derivative of the sine is cosine. The derivative of the cosine is negative sine. And the chain rule is the derivative of f with g inside times the derivative of g. So we take these and plug it in. We have the cosine with the cosine inside of it times the negative sine. And so do we have anything like that? Well, we have, here's the cosine with the cosine inside of it times the sine, and it's all negative. So that looks like that should be it. And yes, indeed, 28 is option D. And let's see, 29 is a duplicate, 30 is a duplicate. Let's look at 31 then. Let r of t be a differentiable function that is positive and increasing. Okay, so we know it's positive, it's above the x-axis. We know it's increasing, which means it's going up as x increases, y increases. The rate of increase of r cubed, so not the original function, but if you cubed the original function, the rate of increase of that is 12 times the rate of increase of the original when r of t is basically saying at what value of y. And it is not asking us at what t, at what x value. It's asking us for the value of y. Where do they match? Okay, so what can we do with that? The rate of increase just means the slope, and the slope just means the derivative. So the derivative of r cubed, I really should have wrote d over dt because it's r of t, but we'll just pretend it's r of x, equals to 12 times the rate of the original one, r. So what is the derivative of r cubed? Just do power rule. Bring the 3 down, subtract 1, and that would be 12. What's the derivative of r by itself? It's just 1. And, yes, we're using r to stand in for some entire function. We don't even know what that function is. We don't know how we would take the derivative of that function, but just do it this way, and it still works. So you have 3r squared equals 12. Obviously, the one is superfluous, so we can divide both sides by 3. R squared equals 4, and then take the square root. R equals, and well, technically that would be plus or minus 2. And we're still working with just the original function where we didn't even get into the t at all, just where r equals 2 or possibly negative 2, but we're only, well, it actually says positive. We can disregard the negative 2 because we know it's positive. But negative 2 isn't even an option, and positive 2 is, so we just call it 2, and that is indeed the answer, selection B, for there. Okay, well, we got to 5 whole questions on this sheet. On one sheet, see, some of these pages are loaded up on duplicates, but we got 5 whole new questions on one sheet. That's great. So number 32 here, the derivative of a definite integral. Isn't that interesting? Definite integral from 1 to x of t squared dt. Okay, so this is the kind of thing that we just want to take in pieces, one at a time. 1 to x t squared dt. So let's do the definite integral first. So the integral of t squared, power rule. So how would we reverse that? We subtracted 1 from something to get to t squared. So that would have been t to the cubed. And to take the derivative from here to there, we would have brought the 3 down, multiplied it by something to leave us with 1. So that's got to be a third. So we take that and plug in values. With the definite integral, we plug in the upper bound and then subtract with the lower bound plugged in. So 1/3 x cubed minus 1/3 1 cubed. And we can just call that 1/3 x cubed minus 1/3. 1 cubed is 1, goes away. And now what is the derivative of that? So we just go through it again. Power rule. 3 comes down. 1/3 times 3 is 1. Subtract 1 from there. We get x squared. 1/3 doesn't have a variable there. That goes away too. So we just have x squared, and it kind of seems like we went full circle there, doesn't it? Just end up where we started. You almost expect this to be trickier than that. But x squared is indeed a selection, and x squared is indeed the answer. If there was one more complicated than that, you would just go through the same process and maybe end up with a more complicated answer. But probably the idea here is they want you to second guess yourself. Oh, it can't be that simple. But yes, it is. Okay. That's it for that page, and that's it for that video.